Hello everyone, and welcome back to the Kohi Game Engine series. Today we are going to talk about multithreading. So before we jump into the video, I would like to take a quick minute and thank the partners of the channel. The partners are the highest tier of support both on YouTube and Patreon, and they are Caden, Eearslya, Gerboles Inc., Super Awesome, and Wensheng. I'd also like to thank all the other fine folks that appear on the screen here. Your support is greatly appreciated. Thank you very much. If you'd like to support the channel and support my work, feel free to have a look at the YouTube membership, or if you prefer Patreon, you can check out patreon.com/TravisVroman. So, multithreading. This is a topic that is very difficult for a lot of people to sort of grasp and understand and get right. And it's one that we're probably going to be touching on multiple times throughout this series as a result. Because it's not really something that you sort of set and forget unless you happen to get it right early on. So chances are that we may touch on this a few times over the next couple videos, just because some of the concepts here are a little bit difficult to grasp if you've never dealt with multi-threaded programming before. So before I get into multi-threaded programming, let's examine the word multi-threaded to begin with. So multi-thread, meaning we have more than one thread. Well, what does that mean? What is a thread? To understand this, we basically need to understand the way that processors work in general from a high-level perspective. Now, I'm not going to go into a super deep dive here, but basically the way that processors work in general, and there are exceptions to this, is that you feed the processor instructions one at a time, and it executes those instructions one at a time. Now, there are various optimizations that can happen that can cause processors to do things out of order because maybe the compiler determines, hey, we could do this at one operation before we do another one, and maybe it would be a little bit more efficient. So there are some of those corner cases that do exist. There's quite a lot of them. We're not really going to touch on that, at least not yet, because we just need to understand the basics of it first. So when we talk about the way that processors work, we have commands that are fed to the processor that are executed one after another, right? You typically provide some sort of an opcode, and then potentially, depending on what it is, some data that goes with it. Whether that's moving data back and forth around registers or doing some sort of mathematical operation, what have you. Doesn't really matter. And for the longest time in computers, there was one sort of channel that you could go through, that everything had to execute through that individual channel. And processors were this way for most of history. It's only somewhat recently where we have really dived into having more than one of those channels. So before I get into that, let's talk a little bit about the evolution of processors, right? So processors basically had pretty regular speed increases throughout the 90s and early 2000s, where we were just seeing processors that were just going up in gigahertz, and they just kept going up and up and up. And basically, Intel, AMD, they basically just kept throwing more and more and more into speed. But they ran into a problem basically known as the heat wall. And you guys can look this up if you are interested a little bit more about that. But basically, there comes a point where the processor is trying to go at such a fast clock rate, and it's generating so much heat that you actually can't keep it cool. I think Intel had a processor that they had developed that was supposed to run at 8 gigahertz, and it basically just all but spontaneously combusted. It basically just completely melted itself, literally. And so they ran into this issue where they couldn't really make processors go any faster because they couldn't keep them cool to actually run that way. And so they had to start looking at other ways to make things faster because they'd hit a wall there, literally called the heat wall. And so what they started investigating was the possibility, okay, well, if we can't go, fast in one lane, then how about we open it up to more than one lane and we go wide? And that's where the concept of multi-core processors came from. And so today, it's pretty common to see multi-core processors. In fact, single-core processors are extremely rare. I don't even know if they're made anymore, to be completely honest with you. I haven't looked. But basically what you wind up with is you have a processor with multiple cores. And each of those cores is able to take its own set of instructions and process on its own. And it's able to do so independently of the others. And so you might have a dual core processor or a quad core processor. You guys may have heard these terms. And so basically what that means is that you have a certain number of physical cores available that are capable of processing. Now you also have something called hyperthreading, which basically turns one core into two cores. And it's not exactly that because it's not technically a full core all on its own. And so you have this concept of physical cores and logical cores. And most processors out there, most physical cores have two logical cores. And so we're looking at the system monitor here for my machine. And we'll see here that we actually have 32 cores. Half of these, I shouldn't say half of them, I should say the processor that I have is a 16-core processor that is hyperthreaded. So each individual physical core has two hyperthreads on it. And that is what gives us this 32-core count, right? And so, if you guys open up the task manager on Windows, you may see multiple of the bars that they have going across the screen indicating CPU usage. And that's what each one of those represents. It's a logical core. And so basically the idea is that with each one of these cores, you could potentially launch a thread to do some work that needs to be done at the same time that you can be doing something else. So let's say, for example, we need to do a bunch of processing of data, and we can split that data up into, say, two different chunks, for example, to be processed. And what you can wind up doing is having that split between two threads and essentially completing the work in about half the time. Now, it's important to note that threads are something that is sort of controlled by the operating system, so it's like a kernel level thing. Whereas some of the other constructs that we're talking about are not necessarily so. So threads are usually controlled by the operating system in terms of interrupts and things like that. And like I said, I'm not really going to go. I don't really want to go too deep level because this is a conversation that could literally last hours if we wanted to talk about it. But basically, each one of these cores could become its own separate thread of execution. So if we wanted to split the workload or handle multiple things at once, that's generally the way that we would handle it, is by utilizing the cores available on the system. So when we talk about multi-threading, we're talking about doing work across different threads on the CPU. And there are a lot of gotchas that can happen with this, because if you have a central set of data that's being modified, you can technically wind up in a situation where you have more than one core trying to modify or access that data at once. And you can wind up in situations where data might be being updated at the same time that another thread is trying to actually access it. And so if that winds up happening basically at the exact same time, the thread trying to access that data could have an old copy of that data because it's still cached and hasn't actually been updated yet. And so there are things that you have to put in place to actually kind of control access to that data, that centralized data from different threads. Now, I know this is a lot to take on, and so we're going to, like I said, split this up over multiple videos, but we are first going to implement the concept of threads, and then we are going to implement the concept of mutexes, which is short for mutual exclusivity. And that basically puts a lock around certain sections of code that is accessed from multiple threads to allow us to not have those sort of what's known as race conditions. And so what we wind up with, or what we're going to wind up with, is a system that allows us to do multiple things at once, such as loading up meshes or loading up textures, things like that. So we can dole those out to different threads on the CPU, and then sort of gather that data back when all those things are done. So typically speaking, you would have, in most applications, if you were splitting the workload among threads, you would do something that basically starts the work on that thread. So you would essentially provide a function to that thread to be executed, and when that function is complete, it would actually return, the thread would terminate, and then you would be good to go. And generally what you would do is you would call something called joining those threads back to the main thread. And basically the join happens when that thread is complete. So you could wait for all threads to complete before you actually continue executing on the main thread, or there's other ways that you can actually handle that. And so we're actually going to look into some of those other ways. We're not actually going to be joining threads. So for those of you wondering about joining, we're not going to be doing that. We're going to be doing something called detaching. So with that said, I think probably the best thing to do at this point is to, I guess, talk a little bit more about the main thread versus other threads, and then we'll jump into some code. So as I mentioned before, processors in the past only had a single thread, and that became known as the main thread once we started talking about multiple core processors and multi-threading. And so generally speaking, when you launch an application, you have a thread that is given to that application by the operating system, and that is considered the main thread. And that's, generally speaking, that's the thread that main was executed on. And then if you open up other threads from that main thread, you would join those threads upon completion back to the main thread after they finish executing their stuff, and then you're good to go. Game engines don't typically use threads that way because there is a little bit of overhead in starting up and shutting down threads. And we actually don't want that because we are going to have lots of things that have to run. And we actually probably should have a term that we're going to use to describe those bits of code that need to be run on separate threads. And we're going to call those things jobs. And we are going to be building a job system, and it's going to be a multi-threaded job system. But before we can get to that, we actually have to build the underlying part. So all that to say is we will have a job such as loading a texture or loading a mesh or something else. And we will hand that off to the job system. The job will say, okay, let me pick a thread that is currently not doing anything and assign the work to that. And then that will let me know when it's done. And then we can go ahead and perform some sort of callback or notification within the main thread to say, hey, the work on this is complete. But the thread itself, the job thread, never actually shuts down. So again, we're going to retouch on that once we get to the job system. But for right now, all we're going to do is we are going to create the platform version of those threads. Now, I mentioned before that threads are something that is given to you and controlled by the operating system. So that means that it is a platform-specific implementation. So we are going to start with the Linux implementation of that. And in probably the next video, we will go ahead and do the Windows implementation of that. So with that said, let's go ahead and start looking at what we need to do for threads. So I think probably the thing that makes the most sense is to define what the interface for a thread looks like first. So I'm actually going to collapse some of this other stuff here we don't need anymore. I'm going to go to engine, source, and we'll put this in. We're actually going to put this file in core, and this will make sense in a second. So we're going to create a new file. We're going to call this kthread.h. And this is what is going to define what our threads actually look like. So obviously we're going to have a pragma once, and we're going to use our defines. And we're going to define something called a kthread. And the way that this works is each thread has a numeric ID that's assigned to it, and the numeric ID that's assigned to it is different for Windows and Linux, as well as the internal data, and the way that it manages that is different for each one of these. So we're going to use a void pointer to represent the internal data, because the objects that get created for a thread on Linux are different from the ones that are created on Windows. And so this is all a kthread is, right? It just it's a container for our internal data and a thread ID. And so we also need something to give us a definition of what work for a thread looks like, right? I mentioned before that when you start a thread, you have to give it a function of work that needs to be done on that thread while it's active. And so we're going to define a function pointer called pfn thread start. And it's going to take a void pointer, which means it just takes sort of an unknown set of arguments. So that could be any sort of structure that we want to pass in, which is really convenient. And then it returns a U32 as to the results of that thread. And that varies by platform as to what is actually returned there. So we're basically going to pass a function that returns type U32, and that takes a void pointer whenever we start a thread. So we just want to go ahead and define that so it's well defined. And the next thing that we're going to do is we're going to have a create function. So whenever you create a thread, you have to have the start function pointer because it has to have some work to do. Otherwise, it's just going to terminate, right? You can't start a thread without actually having some work for the thread to do. So we'll pass it that. We'll pass it some void parameters, and that can be whatever we want it to be. And then we have this auto detach here, which indicates if the thread should immediately release its resources when the work is complete. And in general, we're not going to be doing this, but I wanted to provide the functionality if for some reason we ever wanted to have the ability to detach a thread automatically when the work is complete, we could do that. We don't want to box ourselves in there. And then, of course, it takes a pointer to hold the created thread. Okay, so since we have a create, obviously that means we have a destroy. It just takes a pointer to the thread to be destroyed. We can also manually detach threads. So that just means automatically releasing its resources when work is complete. So this detach is essentially what we're going to wind up doing because we don't want the main thread waiting on our job threads. Our job threads are going to run in perpetuity. And so we don't actually want our main thread to be waiting on that. So we're actually going to wind up doing this detach. Okay, and that means that basically that the thread continues to run in the background, but the main thread is no longer associated with it. It's not held up by it. It's not waiting on any sort of join or anything like that, right? We could just sort of detach it, let it do its own thing, and then we can just update or use messages to send updates back and forth between the threads if needed. The other thing that we want is the ability to cancel a thread or cancel the work on a thread, if possible. Now, I say if possible because it's not always possible to cancel the work on a thread. It is up to how the logic for that thread is actually written as to whether or not it can actually be canceled. So basically what this does is it kicks off a signal to the thread to say, hey, if you can cancel, do it. And then it's up to the code within that to know how to do it. Now, one thing that I should mention, since we're talking about threads shutting down as well, is whenever you exit the application, that also kills all the threads that were spawned, regardless of whether they were detached or not. So the operating system knows about those things and knows to clean those up. So we don't have to worry about that being an issue. We also have a method here to indicate whether or not the given thread is currently active, aka doing work or anything like that. We probably won't be using that all that much, but there you have it. We also have the capability to sleep on a given thread, so we can provide the thread and then a number of milliseconds to sleep, and that changes per operating system as well, in terms of how that works. And then finally, we have a function to get the thread ID. Now, this get thread ID returns the ID of the thread currently being executed on. So you would want to call this from the current thread that you want to get the ID for. So we're definitely going to need that for our job system, but there's not really going to be a whole lot of use outside of that. And so this is the sort of interface for our threads. So we've put the interface here, but I did mention that this is a platform-specific thing. So the actual implementation of this is going to wind up being in the platform code. So that is the thread. I think probably the next thing to do would be to go ahead and create the mutex, because I think that probably makes the most sense to go ahead and handle next. So I'm going to go ahead and under core create a new file, mutex.h. And a mutex, as we talked about before, is about mutual exclusivity on resources. So this is used for synchronization purposes. And we want to, basically, as it says here, use to limit access to a resource when there are multiple threads of execution around that resource. So mutexes are the way that we do that. And as with threads, this is also an operating system level thing, or platform specific thing. So we're going to define our interface here, and then we're going to implement that on the platform layer. So we have our kmutex create, which just creates the mutex. We have a destroy here, which is pretty self-explanatory, I think. And then we have a lock, which is basically saying any code after this lock, we want to block other threads from being able to do anything with this until we unlock it. And so that is the way mutexes work, is they are essentially locking. And then we have a mutex unlock, which then says, okay, well, we're done with any work that needs to be synchronized. Go ahead and unlock it and allow other threads to obtain a lock. And so as you can imagine, mutex locking is something that can slow your application down if not done correctly. And so you want to limit how many times you actually lock, and you want to limit the scope of code that you are locking, because the less code you are locking, the better. So just keep that in mind. But that is it for our mutex interface. So not a whole heck of a lot there. But yeah, okay. So the next thing to do is we actually need to go to platform. And I think down here at the bottom is probably going to be the best place. So we actually need a way to query the operating system as to how many processors we have. And this is going to be logical processor cores, right? So let's actually be explicit here and say logical processor cores. So this is going to return an i32 to get the processor count, okay? And that is going to allow us in things like our job system to say how many job threads can we actually spin up. All right, so that is it for platform H. So now we need platform Linux, because that's the first one that we're going to wind up doing. And the first thing we're going to want to do is go all the way to the top, and we are going to want to include core kthread and include core kmutex, because we are going to be implementing those here. So what we are going to be doing is, for Linux, the implementation of threads is provided by a library called pthread that we're going to use. And that's for POSIX threads, right? So that's what we're actually going to be using on Linux. And we're probably going to wind up using that on Mac too, but I'm not actually going to implement Mac's threads for right now. So at this point, the Mac version is probably not going to work until I actually get a chance to port it. But I have a feeling that there's not too many of you following along on Mac just yet. So that is coming soon. I don't have one yet. So we include pthread.h. We also include errorno.h because it is the standard error numbers that are provided to us that pthread actually uses. So we use that to catch any errors that may have happened. And then we use sysinfo.h to obtain our processor info. So we need those three includes. So next, let's actually go to sleep, platform sleep, and we're actually going to put our implementation right here after that, since that is kind of where everything else falls into place. So our platform get processor count, there's not a whole heck of a lot to it. So we call this get nprox conf, which returns a number of configured processors, right? So that's our processor count. And then processors available just returns the number of available processors, so configured versus available. And then we just put some information here saying this is how many cores we've detected, this is how many cores are available. So we'd go ahead and just write that out. But what we're really interested in is the number of available processors. So that's actually what we return in this case. And that is all there is, at least on Linux, to get our processor count. So pretty straightforward stuff, I think. So the next thing is we're actually going to start on our thread implementation. So let's start off with kthread create. So the first thing that we absolutely need to do is we need to verify that we actually have a function pointer that was provided, because without that, there's nothing we can do. So we want to return false if there's no function pointer provided. The next thing that we want to do is we actually want to go ahead and create our thread. And that is done by calling pthread create. And what we do is we essentially take the address of our out thread thread ID and we cast that to a pthread pointer, because that is what gets assigned here, right? So this is our new thread. We pass 0 for, I believe that was like attributes. So we're not actually going to use any thread attributes in this case. And then what we're going to do here is take our start function pointer and cast this to the type of function pointer that pthread actually wants. So pthread actually wants a void pointer to be returned. And then it takes a void pointer as a parameter. So we actually just need to go ahead and cold cast that, and then when we go ahead and read the results of that, we go ahead and cast it back. And then some params here. So the params that are passed in here get passed as params here as the last argument to pthread create. And basically, pthread create returns 0 if it is successful. Otherwise, it is some sort of failure. And so we're just going to check for a couple of known types of failures here. So we're going to say if it is E again, it's basically saying that this thread has, or that there's insufficient resources to create another thread. So that means the operating system has said, you know what, nope, you can't have another one. I've never actually seen this happen, but we should probably catch it regardless. We also have something to catch invalid settings or attributes. Now, we're not passing attributes, but if we ever did want to pass attributes, that is what we would want to check against. So we're explicitly checking against that as well. Otherwise, we're just going to output the error code, and we can search up what the error number is afterwards. Now, one thing I should mention is you can always, if you're wondering about pthreads, you should be able to do man pthread create on Linux, and it will actually give you documentation on how to use this. So in case you guys are wondering where I got this stuff from, this is the documentation on how this library works. So it tells you what all the return codes are, gives you code samples, things like that. So just so you're aware of that, you can also Google pthread create, and you'll find a man page online as well. And that is true for any of the pthread functions. Okay, so if, in this case, we successfully created a thread, then we're just going to say we started the process on the thread ID, and we're just going to spit out the thread ID as a 0x identifier, right? And that just kind of gives us the hex of the thread ID. So the next thing that we're going to do is we are going to look at this auto detach property, because if we're auto detaching, we actually don't need to save off the thread handle. So if we're not auto detaching, what we're going to do is say the internal data, we're going to allocate space for that. So in this case, it's just a U64. And then we're going to take the thread ID here and store it in the internal data. If we're detaching it, we don't really need to do that. But if we are, that's basically ultimately how that works. And if we take a look here, we have an unsigned long pthread t. So it winds up lining up with those types. So if we're auto-detaching, we don't bother saving it off, but if we are not auto-detaching, then we do save it. If we're immediately going to detach the thread, then we call something called pthread detach. And again, you can pull up the man page on this. Basically what we do is we pass the thread ID to pthread detach. And then again, just like before, we go ahead and check the result of that. So we have invalid parameters, or in other words, it's not a joinable thread. So we want to catch that case. We also want to catch the case of the thread ID passed was rubbish. Or if we run into anything else, we'll just spit out the error number. So same as up here, we just want to catch a couple specific common cases and then have everything else sort of in a catch-all. Okay, so if we get all the way to the bottom of this and we haven't had any errors yet, we're going to go ahead and return true. And that is our thread created. So there's not a whole heck of a lot code-wise to actually standing up a thread, thankfully. The next thing that we have is our destroy, and that's just going to call our kthread cancel, because cancel is actually what winds up cleaning up a lot of our resources and whatnot. And so instead of running that code twice, I'm just going to have this be a pass-through, in this case, to the cancel method. So the next thing is kthread detach. So this checks to see if we have internal data. Whoops. And if we do have internal data, then we go ahead and we call our pthread detach as we've done before. And so this is very similar to the code up here, except this is just being done without storing it, so that's why we have it twice. This is basically the same thing, it's just now we have stored it. So in this case, we'll need to do a platform free on the thread for that. So our detach is there. Next is going to be our cancel implementation, and for this, I'm also going to paste this in because this follows a similar pattern as to what we've seen before. So it first checks to see if we have internal data. We call pthread cancel against the internal data. If the result was not equal to 0, meaning it was not successful, then what we do is we go ahead and switch on that result, get the error. So if, for example, if we fail to cancel the thread, this one right here, I forget exactly what, this is no thread with the ID could be found, right? So again, if we're not able to find that thread ID, then we need to bleat about that specifically. Otherwise, everything else can just kind of go into the catch-all. We free our memory here, zero out the internal data and thread ID, and that is it. So our cancel sort of does the same cleanup for us that our destroy would do. That's why we just pass this through. Next, we want to go ahead and check if the thread is active. Now, the way that I'm going to do this for now is to just check to see if the internal data is set or not. And this technically will fail in the case of us detaching a thread. And so I put a to-do in here to find a better way to verify if the thread is actually working or not. But for right now, this is what I'm going to go with, right? So if the internal data exists, then we'll say, yeah, it's active. If not, then no. So kthread sleep on Linux is literally just platform sleep milliseconds, right? We don't actually wind up using the thread here. I don't think there's a better way to actually do this. So for right now, I'm just going to call sleep. And generally speaking, this kthread sleep should be called from the thread that it's being executed on. And so this sleep will apply to that thread. So as long as you bear that in mind, you should be good to go. And then finally, we have the get thread ID, which just returns pthread self. So again, this should be the identifier of the current thread, so it should be called from the thread that is currently on, and then it just returns that casted to a U64. And that is the end of threads. So there's not a whole heck of a lot to it, like I said. It's more so just understanding the way that the pthread library works. Next, we're going to tackle mutexes real quick. So we have our mutex create. And of course, this works the same way as before. If we do not pass anything in out mutex, that's a failure. The next thing that we need to do is we need to initialize the mutex. So that is pthread mutex init, right? And again, we can look up the manual pages for these if we need to understand how they work. Basically, what this does is it returns a result that should be 0 if it is successful. Otherwise, if it is non-zero, it is considered a failure. And so in this case, we are passing a pointer to the mutex and then any attributes. And in this case, we're also not using any attributes, so we're just passing 0 there. The only other thing for mutexes we need to do is we need to save off the handle. So we do this by setting the internal data to platform allocate the size of a pthread mutex t. And then we go ahead and we set that here to the mutex, right? So we just copy that data in by dereferencing internal data and setting it to mutex. Finally, return true. So that is all there is to creating a mutex. It's pretty self-explanatory stuff. So the mutex destroy, I'm actually going to just paste in here because it's actually not all that complicated. So first we check to see if we have a mutex to actually destroy. We call pthread mutex destroy. This works just like all the other functions, right? You just pass the internal data. It should return a 0 result. If it does, we have successfully destroyed it. I put a trace message in here. If for some reason we wanted to trace the destruction of those, we can do that. We could also add that to create if we wanted to, or any of these other functions. But for here, I just kind of put it in there for just for the sake of having it. So we're also unable to destroy a mutex if it's currently locked or being referenced. So we want to throw an error if we try to destroy a mutex that is currently locked. If we have invalid values specified by the mutex or attributes or anything like that, it will throw this. Otherwise, we just kind of have our catch-all here again. And then once we destroy, we also need to free the internal data and 0 it out. So again, this kind of just follows the same pattern as what we already have. All right, so now for our mutex lock. Our mutex lock is not complicated either. Most of this is just error handling to give us a little bit of feedback as to what's going on. So again, obviously, if we do not provide a mutex, that's an error. Again, we have a non-zero result from mutex lock is a error. So we just pass our mutex internal data to pthread mutex lock to obtain a lock on the code going forward. And when we actually put this into use, that'll make a little bit more sense. We analyze our results. Again, we have some debug code here if we need it, as well as error code here if we need to debug any of that. So we have our lock. That means we need an unlock, which is basically, again, the same thing. So all this does is, again, make sure that we have a mutex, make sure that it has internal data. If it does not, it turns false. Checks the result of the unlock operation. Again, 0 is success, non-zero is an error. So we try to say, we try to catch a couple of common errors here. So we're unable to unlock if the owning thread is terminated with a mutex still active. So if you obtain a mutex lock on a thread and then you terminate that thread without unlocking it, you'll get this. And then in this case, unlocking the mutex can only be unlocked. A mutex can only be unlocked by the same thread that locked it, which makes sense when you think about it, because otherwise, if you have multiple threads performing locks at the same time, how do you know which one to unlock actually first? And that's a situation that you run into known as a deadlock. So this catches if we try to unlock a mutex from a different thread than the one that's owned by. And then, of course, we have our catch-all here. And that is actually it for our mutexes. So there's not a whole heck of a lot in terms of logic here. Most of it is just error catching, to be completely honest. There's not a whole lot of complexity there. Okay. So the next thing that we should do is we really should go to our application, and we should set up and obtain our thread counts, because we're definitely going to need to know that. So probably the place we're going to want to do this, I'm thinking, is, let's see, probably I guess we could go, should we go after the renderer? Let's actually do this before the renderer. We may actually wind up having to change where this is done, but I'm going to do this right before the renderer. So what we're going to want to do is we are going to want to make a call to the platform to say, hey, how many processors do we have? And then we're going to want to subtract 1 for that. And it's really like a logical core count. And we're subtracting 1 because we don't want to count the main thread in our calculations. Because we don't want to spin up as many threads as we have cores, because the main thread is already a thread. So we need to subtract 1 from that. And if, for some reason, this returns anything less than 1, then something is seriously wrong, and we probably should just say, hey, this is a fatal error, and report it and return false and abort the application. If we ever get a 0 or a negative value here, then something is seriously wrong, and we should really look at our implementation there. So I'm going to treat that as a fatal error and return false, and say the platform processor count -1 for the main thread was reported as this. So we need at least 1 additional thread for the job system. Now, mind you, this is subtracting 1, so we could wind up with a 0 here on a single threaded system, but Again, I haven't seen a single threaded system in quite some time, so I don't think there's any need to support that. But all of our code going forward actually kind of relies on that. So what I'm going to do for now is treat it as a fatal error. Otherwise, we'll say this is how many available threads we have. Now, in my case, my machine has 32 of those. That's kind of ridiculous. Like, we don't actually need that many. So I am going to cap this at 15. And I may wind up actually reducing this to like 7 or something like that, because I don't really think we need to have that many threads at once. But at least with the Sponza loading all the textures and stuff, I actually have seen all of them get activated with 15. So 15 is what I'm going to go with for now. And we're going to say, hey, if the thread count is greater than 15, we're just going to clamp it. And we're going to make a note here saying we're going to cap it at 15, right? And so we'll go ahead and cap that if we need to. And this will all be used for our upcoming job system. So that's going to require what we need here. So I think this is going to be the place to put it. I may, like I said, I may wind up having to move it to after the renderer. We'll see when we get there. In case you're wondering, yes, I'm hinting at multi-threading the renderer. So, all right. Okay. So the last but not least update that we need to make is we actually need to update our memory system. So k-memory. So when we're doing allocations, remember we sort of set up one large arena, and we are managing the allocations ourselves. We're managing the free list ourselves. We're managing all of that stuff ourselves. And so when we are doing that, if we start doing that for multiple threads, we're going to have consistency problems with the free list, especially because we're going to definitely run into situations where the free list is being accessed by more than one thread, and those updates aren't going to happen correctly. So we actually need to go ahead and put some mutexes, or actually just one singular mutex, in our memory system to prevent that from happening, so that when we actually go to access or make allocations from multiple threads, that we don't run into an actual issue with that. So the first thing that we're going to do is come up here and say, right after string, we'll say include core k mutex. And we'll want to handle this, in initialize is where we'll actually wind up creating the mutex. So probably right here at the very end, after we've done everything else, is where we'll go ahead and do that. So we'll say, we'll create our allocation mutex. Okay. So in fact, oh yeah, I need to add allocation mutex to our state. So our memory state is going to have a new property added to it. K-mutex, allocation mutex, and then we create that within our initialize right here. So if that fails to create, we bleat about it and we boot out, because this is not going to run properly without that mutex in place. Okay, so that is the creation of that. So since we are creating that, we need to also come to shutdown, and we need to make sure that we destroy the mutex. So right before the dynamic allocator gets destroyed, we're first going to destroy the mutex. And then we just need to basically wrap our allocate and free functions, or at least the relevant parts, in locks. So the most important portion of this to actually lock is any place where we are performing updates to the state data like this. So right here where we are updating the stats, where we're actually performing our allocation in the dynamic allocator, this is all stuff that would go haywire if we tried to access it at the same time for multiple threads. So we are going to perform a mutex lock right here. to make sure that multi-threaded requests don't trample each other, as I have here. So we're going to lock right here, and we're going to run this code. And then afterwards, we are going to unlock right here. So this is basically saying until this has completed, nothing else can come in here and try and mess with any of this stuff. So this makes all of this thread safe in that manner. So as you have probably guessed, we've done that for kallocate. We need to also do that for free. And so what we have here is, again, we are updating the stats and calling our dynamic allocator free. So this is the section of code that we need to lock. So we'll go ahead and lock that here. And then we will run our code for the stat updates and the dynamic allocator free. And then we'll go ahead and unlock immediately after that. Again, we want to make sure that we lock as little code as possible. And so this is going to make sure that we are thread safe across the board. And I believe that is actually it. So let me go ahead and clean and rebuild. And we can't really test the threads yet, but we can at least execute the application and see in our output what we have. So we've loaded everything up here. If we scroll up, we should have, let's see, where did we put that? Here we go. So 32 processor cores detected, 32 cores available. Available threads is 31. Available threads on the system is 31, but will be capped at 15. So we know that our initialization code is correct. And we know that at least the mutex locks appear to be working, although, again, we haven't really tested that because we haven't tried this on multiple threads yet. Anyway, with all that said, I know that there were a lot of sort of glancing over topics here and kind of keeping things super, super high level. I would like to eventually make a video describing threads, mutexes, things like that in more detail, but I didn't really want to bog down the main series with that because I want to keep this moving. So this is an important feature to get implemented, and this is going to allow us to build our job system. So this is the Linux implementation of this. The next thing that we're going to be doing is we're actually going to hop back to Windows for a second. And we are going to implement the Windows side of this next. And while we're over there, we might wind up just doing a quick pass on some of the code there just to make sure things are all good. But yeah, we're basically going to repeat this implementation just using the Win32 version of this because that is quite a bit different. Believe it or not, it's actually a little bit easier and simpler to work with. So we are going to do that next. In the next video, and then after that, I believe we can actually start putting our job system into place, where we can actually start doling out work to these threads, and start setting up jobs and multi-threading our application. So super exciting stuff coming. I know a lot of you have been asking me about when is the job system coming. It's coming very shortly, and we're putting in the groundwork for it now. So anyway, thank you guys so much for watching. I really appreciate you guys following along with the series. If you have any questions, feel free to leave a comment below, and I will answer it to the best of my ability. Please toss the video a thumbs up if you liked it. It helps me out a lot. And if you haven't already, consider subscribing. And I will see you guys in the next video.